Hey everybody, how are we doing? We got Josephine here, we got Tiffany here, we got Kayla here. So many great questions. We got the shopper question, got the golf club question, organization monitors elementary school questions, junk mail questions. Oh my god, my ears buzzing question. School, let's see right here. Josephine's got the first question. Let's go do it. It is, let's see, let me get my Pearson up. How is everyone doing today? Let's throw out some Mubot points. All these great questions. We got more coffee right now. We got coffee. We got Mubucks. We got everything we could ever want. Jumping in here, getting my Pearson loaded up, turning on a little chill music. Got the chill music playing, right? Yesterday in the first class, we had no music. No music. Sad times. Sad. The first question was... Oh no, Kayla. Max, good to see you here, Max. Good to see you here too, Tiffany. Oh, I'm sorry, Kayla. Hope the kids are doing well. Hoping to lure more shoppers downtown. A city builds a new parking garage. This is going to be some quantitative intervals. I'm trying to unpop my ear. It keeps on humming. Stop humming here. There we go. I'll make those noises anymore. My ear will be fine. And I don't know why my computer acts so weird sometimes. There we go. Is it because I got this in full screen? Might be. Let me close down a bunch of this, or minimize a bunch of stuff, see if this helps. Trying to fix some stuff in the background here, then we're gonna get started. Put on our serious faces. Okay, got a whole bunch of stuff minimized. Didn't help. Well, we'll just deal with it. Okay. Yawn. That did pretty good, Kayla. Pretty good right there. Doing a little bit better. First question is hoping to lure. Here we go. Hoping to lure. Stat 201. Hoping to lure more shoppers downtown. Let's go check it out. Good morning, Colin. Good to see you here. Colin, I demand some pixie dust. Where's my pixie dust? Where is it? I demand it. You know what we're going to do right here. Colin's going to send us that pixie dust right here. We're going to take the info from this question. I'm waiting for it. Colin thinks I'm joking. So here we go right here. Maybe the stonks be. Oh, I get it. It's a stonks / Star Wars reference. I like it. I should have read the rest. So here we go. What do we have now? This is a new chapter we'll be doing tomorrow. And so this chapter right here, we have a what right here. Let's identify our notation. We have a what right here, and we have a what right here. This is a new problem we have not done yet. We'll be doing it tomorrow. So this is a confidence interval for the true mean. I'm going to start writing the equation for you, but I want you to try to identify. Great job, Kayla, right there. 100 points. Kayla's got some of the notation already going. And so now this is the sample size in the problem of how many people we spoke to. And then the remaining portion is usually where people get stuck. The equation is going to help out a lot right here. When we do the equation for this is, great job, Kayla. You are right. This is the equation, and we'll be going very much into depth on it tomorrow. And Kayla's already identified quite a few parts of this. Thank you so much, Colin, giving some points and pixie dust right there. Kayla said this is the standard deviation, but it's for a sample, which Kayla did correctly mark. And what is 130 now? There's only a little bit of notation left. You only got a great job. This is, Kayla, excellent work. I'm going to drink some coffee right here. But that's totally right. That is the sample mean. Y bar is the mean of the Y variable. So we're interested in the average for this group right here. And that is the average. So the big question becomes, well, what is the T statistic? So the T statistic right here is based on the T distribution. Kayla, you know everything. Wow. Great. Kayla made me smile this morning. Everyone's making me smile. Mubot's going to bring us to the T distribution right here. And once again, you'll see this link in the chat. Mubot, I'm on top chat. Kayla, wow, you're super quick. Is Mubot not... I've been giving out points and Mubot hasn't been here. Mubot, you sleeping on the job, man.
I am Mubot.
It's because I don't talk to you as much these days. It's because you're not awake these days. Mubot. We've woken up Mubot. He can now. What's weird, he sees the world before I see it. He sees the world. See, look at him chatting away right there. He's super quick. Mubot's putting in the chat right there. It's Mubot's brain behind us all right there. Mubot, go away. So Mubot has put in the chat the T distribution now, and we're going to head over here, and we got to make up for all those lost points that we didn't give. We're throwing out some big 500 points right here for all those points that we didn't give, that we did give. The T distribution right here is a lot like the what curve. What does the T curve basically look like? The T curve basically looks like the what curve. Like, it's not that curve, but it basically looks like it. It basically looks like the what curve. I'll just talk about it for a half second, right? It looks like the normal. Exactly. Amazing work. It looks like the normal. But the T has with it a special thing called degrees of freedom. So the more degrees of freedom it has, the more normal it is. And if you've been practicing what z-scores are, if the interval we are making is, let's make it here, a 95% confidence interval. With 95% confidence, you would think that the z-score would be very close to 2. And actually, at 60, it basically is 2. Oh, I'm so sorry, Tiffany, you're right. We got to cherish Mubot. So with this right here, as the degrees of freedom get higher, this curve goes towards the normal. As the degrees of freedom get smaller, the curve is more smashed down. But look, small degrees of freedom, larger, huge, crazy degrees of freedom. So the more degrees of freedom you have, the more normal the curve is. So really at this point, it's going to be the same values you would get on the normal curve of 1.96. And it really just depends on how many degrees of freedom you have. So the question you should ask me about this problem is, what question should you ask me? Because we don't have all the notation yet. And the question you should be asking me is this, because that's what we just were talking about. What should you ask me? You should say, Brian, how many whats do you have for this model you're making? Or for this question, there are this many this. For any time we're doing the T, anytime you're doing the T, you should always say, well, what are the whats for this T? And that's the formula for the thing we were just talking about. Kayla might already have the T statistic. And so that is a T with, and so what this stands for down here are, these are the degrees of freedom. This is the formula for degrees of freedom. And the degrees of freedom for this are 44. And look at it, it's n minus 1. Kayla, I don't care. I'm throwing 1,000 points. You are super impressing me today. Did you already learn or practice this or go over I'm not giving points very well today. Kayla, amazing work. You are very on track with what you need to know with this, and you're ahead of schedule. Very impressive. I don't say that lightly. Like, you're finding the T, you're getting the numbers, and so now it really becomes a plug and chug into the problem, because there are, what did I say, 40 what degrees of freedom? 44. And we need to make sure, so there's the degrees of freedom. Now we need to say what percent confidence are we building? Here we're building it. It's 90%. So Kayla's already got that. I can tell. I was like, wow. I was like, you're like, here's the answer to this. Here's the answer. Like, great job. 90% confidence. I like to shade the middle. When you look at this, say, is that 90% shaded in the middle? Yes, it is. There's my T statistic, and there's my degrees of freedom. Let's make a checklist. Is this 90% confidence shaded in the middle? Yes, it is. That means it's a 90% confidence interval. Best way to view it is this way right here. Do we have 44 degrees of freedom? Yes. Why 44? Because we were doing a sample size of 45. The degrees of freedom are n minus 1. So there's 44 degrees of freedom right there. And that's because n minus 1 for a one sample T. And so, yeah, that's the T statistic right there. Very close to like a z-score of 1.645, but it's a little bit bigger. And that's where sometimes people make the mistake. So now that we have this, we can solve the T interval. And Kayla said it's 1.68. So 1.68, you don't multiply by that n minus 1. It's just notation to say the degrees of freedom are n minus 1. Now the standard deviation is 18 divided by the square root of 45 plus or minus 130. I try to throw out bigger points so more people impress me, and that was excellent work. Like, you're totally solving this problem along, and that's what I like. That's where people know how to do it. We're just going to solve this out. What I'm solving right now is the standard error, so I square rooted that. I'm going to copy it. 18 divided by, that's the standard error, which is this portion right here. We're going to multiply this by 1.68, and I want two letters. What did I just find by finding 4.5? 4.5 is the what for this interval. What did I just find by finding 4.5? So it's like 130 plus or minus, I think it's 4.51 when it rounds. So it does round to 4.51. This is the what. Important things to know about this interval that we have right here, everything here, which goes into this margin of error. Yep. And then the first part of it is the center of the interval. So we estimate the whatever it is to be 130, and that they'll make 130 with plus or minus 4.51. So we can write the upper and the lower now, which is probably going to what it's going to want us to find right here by adding and subtracting. So this is the final solve right here. The upper number is pretty easy because you can just straight add those numbers without worrying about subtracting. We'll double check our work. We can do it in our head too, but we'll take 130 minus this, and that's the lower. So 125.49. And that's the lower. So 125.49. 125.49 and 134.51, I believe. Taking a quick look again, 135.41. The conditions for this are random. Did we randomly select the data? So the data should not be dependent. That would not be random. So this one's tricky because they're really trying to mix up the way they ask you these questions, not to ask you the same thing 50 times. But if the data were dependent, that would not be random. The data are a random sample. That's good. That is random. This one is not random. The sample is at least 10%. Do we want to do that? Yes or no? Should I check this or not check this? The data is at least 10%. Should I check this right here? Should I check that, yes or no? The conditions are random, something about 10%. We want it to be what to 10%? Needs to be less, exactly. So don't check that one. And then we want the data to be unimodal symmetric. That's the nearly normal condition. So condition 1, random. Condition 2, less than 10%. And condition 3, nearly normal, which it's stating the condition right there for you. Explain the correct context of this interval. I am 90% confident that the true daily income 90% of the interval contains the mean daily income. Ooh, it's tricky. Oh, oof. Okay, it's saying this. These are just flipping these right here. I'm trying to see the difference between these two. I don't like the word fall. I've never liked that. I'm going to be really mad and scream at my person. Let me look at the difference between these two. There's 90% confident. Do I have my interpretations up from yesterday? I might on here somewhere. I like to say I am 90% confident that the true mean income will be contained in the interval blank to blank. So here's the mean daily income. I almost feel like false, and I don't know if they're going for that. Oh. Well, that makes it easy. Kale, 100 points. Always fall in the interval. That's weird, right? Yeah, it's just weird. I am 90% confident the interval contains the true mean. Yeah, that sounds better. I was like, it looks like D, but what's wrong with C? Yeah, will always fall in the interval? That always is. No, it's not how we talk about it. Explain what 90% confidence means. 90% of 90%. Kayla, great. You're acing it today. I was like, I don't want to get this wrong. I was like, I feel like it's D, but C is making me think, what's wrong with C? 90% of random sample size of 45 will produce confidence intervals that contain the mean. This goes back to the theory we were doing yesterday. So we've got some confidence interval theory here that if we build multiple confidence intervals, basically the repeated process of building confidence intervals, 95% of 95% confidence intervals are expected to contain the truth. That's what this is getting at. There is a sample size associated with this one. So we would say 90% of sample size 40s will make intervals that contain the truth. So we should be right there, and we'll produce confidence intervals. Yep. Since 90% confidence interval, they want to know about 129. Do you think 129 is a possible value? Does 129 seem to be a possible value of truth? What would we say to them? Since the confidence interval contains that value, the consultant's prediction seems plausible. So I would say yes. Check answers, 100%. Kayla, another 100 right there. Kayla made sure we got 100 right there. Amazing work, Kayla. We're going to do the next question right here. Kayla, you know what? Well, let's see. I think Tiffany had one. Then we'll do Kayla's question next. Amazing work. Tiffany has one, and then we're going to do Kayla's question. Thank you, everybody. Let's keep going on right here with all these questions. Really great practice. That's what it's all about. Wow. When you're like catching errors, I'm like double checking. You got it down. And here's the great thing. Test 3 material is very, very much the same thing. Like a lot of intervals, lots of testing. So what you're doing right now is like going to be very consistent. Yeah, Kayla, that's awesome. Excellent work. How far do... We'll Josephine. We'll hop back and do Josephine's second question here. We'll do Tiffany's, and then we'll jump back. We'll do Tiffany, Kayla, Josephine. And so an organization monitors the aspects of elementary schools. Attendance. Okay, so this is... I think Tiffany's doing hypothesis testing. So we're going to get to see Tiffany. Great job. I think Tiffany's doing chapter 15 hypothesis testing. Or chapter numbers are weird these days. I believe this is chapter 15 hypothesis testing. I believe so. This one has a good bit of a trick in it too. We're going to do some oh, there it is. Just saw it. Hypothesis testing. Okay, let's do some hypothesis testing right here. Chapter 15, hypothesis testing. New stuff. I know, right? I was like, I know that question. It's hypothesis testing. Let's check it out. This is a fun one. I like this one. Oh, wrong button. Wrong button. I hit 3 wrong buttons. Okay. So when we do hypothesis testing, we have to know what a null hypothesis is. This notation right here, HO, stands for the null hypothesis. This notation right here stands for the alternative. It's not that bad. Think about this. If you were to go to be put on trial, what would they assume about you with no evidence? With no evidence, what would they assume? And this is what a null hypothesis is. A null hypothesis means like nothing at all. Nothing at all. So if they had no evidence, what would they assume about you? And then they would try to show evidence of this. What would they assume about you? If you go on trial, they will assume something about you, which is the null hypothesis. That you're innocent. Now, I'm going to tell you a trick for the null hypothesis when we write it in notation. And we'll say this a lot in class, so you're getting ready for class right here with this. The null always has the equal sign. The null always has the equal sign. So we're always going to assume that a certain value is equal to something. So tell me, what do you think the answer is to the null hypothesis here? If you know that the null always has the equal sign, I'm pretty sure you can get this right. Is it option 1, 2, 3, or 4? And then we'll explain what this means. Which of these looks like the null hypothesis for this question? 1, 2, 3, or 4? So the null always has the... There you go. And that stands for that the true proportion is equal to 38%. We're talking about children having perfect attendance at a school. Now, officials would be interested if it's declining, but do these figures give evidence that it has changed from 38%? Great job, Tiffany and Kayla right there. Do these figures give evidence that it's changed? I want you to keep this in your mind, that the alternative is the evidence-based claim. We're looking for evidence it's changed. So option 1, 2, 3, or 4. We're looking for evidence that it's changed. Be very careful. The question will always tell you which way the alternative goes. So the alternative is the evidence-based claim. We're asking, is there evidence it's changed from 38%? And you have to read the question and say, do these figures give evidence of a change in student attendance? That's what they're interested in researching. Is there evidence of a change? This one's tricky because it does say it has declined. And of course, they'd be interested if it has declined. But is there evidence of a change? They are looking to see if there's evidence of a change. So which of these looks like has the true proportion changed from what it was previously? I didn't select the right answer yet. So option 1, 2, 3, or 4 would be us talking about has it changed. I think you're right, Tiffany. Option 1, 2, 3, or 4. I think you're on the right track. And then we're going to talk about it in words. Exactly, Kayla. Yep. So what this says is that the true proportion is not equal to 38%. Don't read this as P. It is P. But does that make sense to say the true proportion? Great job, Tiffany and Kayla. Both of you do an amazing job. But does it make sense to say the true proportion of students with perfect attendance is 38%? That's what we're assuming to start. Then we're looking for evidence. So always talk about the alternative as like, what are we trying to see if there is? We're looking for evidence that the true proportion of students with perfect attendance is no longer, i.e. not equal to 38%. Just try putting it in words like, well, it was 38% historically, but has it changed? Is it no longer equal to 38%, the true proportion of students with perfect attendance? Condition 1, I love it still, is random, which is basically independent. Yeah, sure, it seems plausible. Are these random kids? Sure. 10%, are these less than 10% of all elementary school kids? I'd say so. 9,000 about is probably less than 10% of all random, I love it too, of all possible kids. So I would say that's plausible also. Now the success failure condition, you're going to hate me for this one. It was NP, NQ. Then yesterday it was NP, NQ hat, NP hat, NQ hat. But today it's NP naught, NQ naught. This right here is P naught. This is the hypothesized truth. And we think that the hypothesized truth right now is equal to P. So with the way we write this right here, I'll show you the without numbers in here. I'll spell it right here. Great question, Kayla. Thank you so much for asking these questions. The null hypothesis states that the true proportion is equal to some hypothesized proportion. The alternative hypothesis states that the true proportion, at least in this instance, is not equal to some hypothesized. So right now, we are stating that we currently believe that P naught is equal to P. So if I write right here the following, NP naught greater than or equal to 10 and NQ naught greater than or equal to 10, P naught is basically like using P. Does that make sense right there? We're saying right now we believe at this moment that P naught is equal to P, and P naught is what we're hypothesizing is true. So if we're saying I believe at this moment, I'm just saying right now, hey, it's 38%, and I think 38% is the truth. So we would use it as P, because we currently believe. It's called not like naught. It's called not P naught. I think it's like the null. This is the null hypothesis, H naught, H null. I don't know how to talk. It's my ear popping. That's what I'm going to blame it on. So that is the null hypothesis. That is what we have right there. And it is satisfied. We would take 38% of, there's n of 8955, times it by P naught, which is this. Can you find me Q naught? Oh, I'd love it if this was a test question. So here's P naught. Here is P naught. Could you tell me Q naught? What is Q naught? We will need, yeah, like you, maybe double check it. I don't spell these things. I just talk about them. Great job, Tiffany, right there. Q naught is 62% or 0.62. So remember, they're always complements. P, Q, P hat, Q hat, P naught, Q naught. We use P naught and Q naught when testing because we hypothesize. P naught butter. So this is passed. There's no plausible on this because it is passed. We can check that one mathematically. Now, this is where things get a little bit crazy. We're not making a confidence interval with this z-score. This is not the z. There's no confidence level for this. This z-score is going to be from the following equation. Remember, this is a new chapter we'll be doing next week. So if you're watching this right now, currently, later tonight, maybe you're like, what? We haven't done this. That is true. I think I just ate my pen. Oh, there it is. I put it beside the thing. Could not find my pen. Okay. And so the equation for this one is z-score is equal to observation of p hat minus p naught over p naught q naught over n square root. Almost like p times q over n square root, right? Which we're assuming p naught is p, so it is p times q over n square root. So all we're doing right here is getting a z-score by finding how far away is our sample proportion from our observed proportion. So let's help ourselves out right here and get the notation, which we're going to need right here for this problem. And let's see if we can identify. Can you identify what we assume to be true? Can you identify what we assume to be true? What was the hypothesized truth? We already noted it to begin with. What was the hypothesized truth? Be careful, I'm trying to trick you. What was the hypothesized truth? what was the hypothesized truth, which is P naught? 38%, exactly. That is the hypothesized truth. So this is P naught because it's the hypothesized true proportion. We'll use it in the P equals P naught part. And then Q naught is the complement of that, which is just the other side. And then this down here is what we observed this year or so from the 8,955. So that has a sample size. So that 37% is the what? Not this, but over. That 37% has a sample size. And it's what we observe. So that 37% is what? Because it comes from a sample size, which is a good indication it is this. It's a proportion that comes from a sample with a size. Is there no orientation? Yep, exactly. It's a p hat. So that is a sample proportion. Now that we have everything marked, we are just moments away from solving this. I'm going to try to get it all on the screen at the same time. Now that we have all this, we're just going to plug in p hat of 0.37 minus p naught of 0.38. We're going to take and do 0.38 times 0.62 divided by 895. That's a 9. It's a horrible 9. 955 square root. And we're just going to solve right here. So the bottom portion is the standard deviation this time, not a standard error because it doesn't come from a sample. Statistics, using new words every time. Good, and then square root. And we're going to get a z-score of about 1.94. 1.94. The top part of the equation is 1%. If you just look at it, it's going to be 1%. It is negative 1%. Good. So it's negative. Yeah, that is negative. Good. And then we divide by this. Negative 1.94. 1.95. So this right here is negative 1.95 z-score. Now, this is very interesting, and I like this. Because when I do the p-value here, two decimals, good. The p-value for this is going to be, I'm pretty sure it's going to be right about that. And I'll show you why. What are we going to do? We're going to go to Mr. David M. Lane. We're almost doing a lecture on this question. This is almost just a full lecture of this question. Because these are new things we haven't learned yet. And let's take a look at how we find the p-value. So to find the p-value, it's going to be super important. Kayla knows what's up right there. It's going to be super important we know the sidedness of the test. So was this a less than, greater than, or not equal to test? Let me ask it this way. Was this a less than, greater than, or does not equals to test? Or does not equals is here. So was it a less than, which we would shade less than it, which means we'd said like P is less than P. Yeah. Yep. I think it's a theory one. We should be able to. I think we got 2 more questions lined up, then we do that one. And then, or was it a greater than test we did, or was it a does not equals to test? And the answer, remember we got a z-score of negative 1.95. Let's put that in for all these values right here. And we have to do the positive version here. We're not actually going to use that one. Oh, it's close. Oh, maybe a little bit closer than I thought. So was it a less than test? Or there's the less than. Was it a greater than test? Here, let's double check how we know. Here's the answer to what it was. Was it a less than, greater than, or does not equals to test? So double check right there. Yeah, if asked what you're stuck on. So was this a less than, greater than, or does not equals to test? Was this a less than, greater than, or does not equals to test? Which of those tests was this? It was a not equals to test. And then knowing what test this is will tell us what? It'll tell us how we shade the curve. So Tiffany, make sure you have this. What am I plugging into this applet? I am plugging in the what into this applet. What am I plugging into this applet? And maybe I should have put the answer over here on the side. I'm plugging in the what to this applet, the z-score. So now we solve for the z-score and we get the p-value. It's different than confidence intervals where you have to get the z-score for the confidence interval. We solve for the z-score. And then how would I know what to do with this? Like I've got 3 options. I'm either going to shade, like here's where the value is at. I'm either going to shade below this value, or I could shade above this value, or I have the option of kind of doing here and doing on the other side and getting a p-value like this. I have 3 options. And these 3 options have different values. They have a value of like 2.5%. And this one is now 97.5%. Look at how those add up to 1. Hints for the test. Oh my gosh. And this one right here is double the other one. So this is 5% about. How do I know which one of these to choose? How do I know, should I shade left, right, or both sides? So this is a repeat question again. How do I know which way to shade? Am I going to shade to the left, to the right, or both sides? Where was that decision made on which way to shade this curve when I do the shading? Where was that made right here? What makes the decision on which way we shade the curve? The what right here? Or keep going. It's a new topic. Don't worry. Just get things wrong. 100 points. Just throw out those answers. That sounds all right. Great job right there, Tiffany. Yep. Your answer's going to be close to mine on this. So that sounds right. Which way we shade the curve. The sign for the, what does this A stand for? This is a type of hypothesis, and it's called the what? The sign for the alternative hypothesis. So if it was less than, you see how this points to the left? We shade to the left. If it was greater than, we shade to the right. Now, we don't use an equals for the alternative. If it does not equals, that points both ways. So if we had done a less than alternative, we would shade to the left. If we had done a greater than alternative, we would shade to the right. Look at the way the arrow points. Exactly. So the A stands for alternative. Yes. No, don't worry. This is why I'm like, if you're stuck, just feel like, I don't know. But we chose this one, and we're going to shade what sides of the curve? For this one right here, we are going to shade both sides of the curve. Does that make sense? We won't shade below that point. So here's if we shaded below it. Here's if we shade above it. We're actually going to take and flip it to the other side and shade both sides. So Tiffany, go to the David M. Lane right here. So Tiffany, I'll show this. Tiffany, here's the answer to yours, so you can work along and follow. But does that make sense, Tiffany? That's the answer to yours right there. If it rounds to 3 decimals, 0.049, 0.049. The answer to mine is very close, is 0.051. I estimated it, and I was close. I was close. And the reason I was close is because it's very close to a z-score of 1.96, and I know the answer is to 1.96 because that's a 95% confidence interval, 95% on the inside, 5% on the outside, and it was very close to that. Now, alpha is the point at which we reject things. So here's the best note to have. And someone put this in the chat, 200 points, I'll throw it out there. If your p-value is below alpha, reject the null. If the p-value is below alpha, reject the null. So if the p-value is below alpha, reject the null. That's the biggest thing you need to know. You look at your alpha. If the p-value is below it, you reject the null. And usually alpha is 0.05 unless we state otherwise. But here it's saying alpha, which what's that symbol stands for, is 0.1. And then we say if our p-value is below alpha, we reject the null. So let's ask ourselves, is that p-value right there below alpha? So you want to look at the p-value. Nice job, Kayla, right there. And here I'll answer right here. We look at the p-value and we ask ourselves, is this p-value right here less than alpha? It is. Reject the null hypothesis. If you reject the null, you're saying, I don't believe this is true anymore. I'm tossing that out. That means we do have evidence for the alternative. If you reject the null, you do have evidence for the alternative. If you reject the null, you don't have evidence for the alternative. And what was the alternative? Was it that perfect attendance has gone up, gone down? No, it was that perfect attendance has changed. So we have evidence for this right here. So what it is the attendance number was far enough away that we are able to reject and say it has changed. Now, this is only a change of 1%. So the difference is probably not meaningful. It's very, very small difference. I think we've done it right there. Yay! So there's only a difference about 1%, which is like, it's only changed by about 1%. It's not a big difference. I mean, we do have evidence that there is a difference here that's not likely by random chance and smaller p-value. We did use a 0.1 standard, which I don't like that. Maybe my person shouldn't be using a 0.1 alpha. Usually we use 0.05, which makes it harder to reject. But really good question right here. And this was a lot of theory. It was almost a mini lecture. So definitely come to class as we go through this and talk about alternatives, null hypothesis, and p-values for finding these tests. Really good question right here. And following through with the steps is how we get it done. We got time for like at least 3 more questions. Tiffany, is it looking pretty good? So Tiffany, your p-value should have been back on the screen a moment ago. And also you should be rejecting the null. You should have evidence that it has changed because this one always does a change. But really good question, Tiffany. Pretty tough, tricky one, especially for doing the testing. Here, stop hopping. Let's go back to the main screen right here. Next question. I think we said Kayla. Kayla's question. Kayla, thank you so much. Hanging out. Had a question at the start. And we're going to do it right here. The direct mail advertisements, junk mail. Is it junk or spam? Direct mail advertisements. Direct mail. Let's hop in here to do some direct mail. It's chapter 13 quiz, right? Replace questions. Hello, sales company. What? I'm just going to yawn all day. Let's go down here to the bottom. Awesome, Tiffany. Great job, Tiffany. Excellent work. Keep it up. I am so proud of everybody working ahead. Oh yeah, it's one of those find the sample size ones. That one's weird. I'll show you the cheat way of solving it, and then we'll do the actual way. I don't love the find the sample size ones. You might be like, Brian says he loves every question. It's just we generally don't do a find the sample size quite. Like, you don't see a lot of them on the test, so that's good news right there. Oh, here we go. Oh, at the very end? Okay, we got this. Okay. Let's go take a look. I'm not a huge fan of those find the sample size ones. Fine. Okay, here we go. Let's hop into the question. A direct mailing is talking about junk mail. Let's go check it out. Oh, we didn't know which number was the sample size. Ooh, good question. Let's check it out. Here we go. New question coming right up. Okay. Direct mail advertisements send solicitation junk mail to thousands of people in hopes that they will buy something. The response rate is usually quite low. Suppose a company wants to test out the new flyer and sends it to 1,050 people randomly selected from a mailing list of 200,000. They get orders back from 101. So I do like this question right now because it is trying to trick you. We've got multiple things right here. There is something we won't use. What is any of the notation? We always mark our notation to start. Yeah, is this one it right here? Look at Ashling, you came at the perfect time. Perfect time right here. So we need some notation. I'm going to write the equation while you write the notation. So we're going to build a confidence interval. P hat, which is the sample proportion. We don't have that yet up here. Plus or minus Z, which is going to be chosen for the percent confidence, times the standard error, which is P hat times Q hat over N square root. Very similar to P times Q over N square root. And so what do we have right here? We're missing some notation. I'll give you hints on what we need. But I want you to start helping me out. Ashling, so good to have you here. Here is some stuff we might need. What do we have and what do we not have? A few of these we won't be able to find yet. Or we won't need. What do we have? Kayla's all ready to go with the David M. Lane. What do we have? Anyone help me out on any of this notation? I've got it highlighted up above. You bet. I think we'll do that next, Tiffany. And then we'll do Muhammad's question. So what do we have next? What do we have in here? Need some help on that notation. Take a... It's not. Good guess right there. Good guess. It's not, though. I'll throw 100 points. Remember, we get things wrong here to get it right on the test. 1,050 people were randomly selected. So that sounds like the what? 1,050 people were randomly selected. 1,050 people were randomly selected. That sounds a lot like the what right now. If I tell you I spoke to 1,050 people. I spoke to 1,050 people. So that sounds one letter in the chat. I went out and spoke to 1,050 people. The sample size, yep, that is the sample size. They're trying to trick you. That's the population size. We rarely put that on. We just don't use it in the equation, so it doesn't matter, Rock. You know what's up. It doesn't matter. Doesn't matter. The population size is not going to be used in the calculation. That's a bit of extra erroneous information we don't need. So then 101 is what? Because out of the 1,050, they got orders from 101. So that is the what? What did they get right there? Out of the 1,050, they got orders from 101. So that would be... I might sell this one. Make sure we get through all the problems. That'd be x. And then p hat is x over n, which is the proportion out of the sample. And that's going to be a little bit less than 10%. It's going to be like 9.4, right? No, 9.6, I say. Yeah, 9.6. I solve math for fun. I think it rounds to that. I'd carry all my decimals. Yeah, rounds out really well. And then we do q hat by doing 1 minus. And so q hat is just 1 minus 0.9038. Hey, Snea, good to see you here. If you got some questions, let me know. Good to see you here, Snea. 100 points, Snea, showing up right here. Now, the z-score, I have to know the what to find my z-score. It's on here. I have to know the what to find the z-score. Great job, Ashling. I have to know the what to find the z-score. I have to, anytime you say, well, what's the z-score for the confidence interval, not for a test. We're doing that a moment ago. You have to know the what for your confidence interval to know the z-score. If we say, let's go make a confidence interval, you have to say, well, what kind of confidence interval? You have to know the what for it. If I say we're going to create a confidence interval, you probably want to ask me what confidence it is exactly. So put in the chat a moment ago, Kayla put this in the chat. To find the percent confident or the z-score, we're going to put 95% and shade the middle, and we get 1.96. So this is the same number every time for z intervals. T intervals will have different numbers. We talked about those earlier today, but this right here, it's the only question. Oh yeah. Have you tried the fancy R plot? Send me your code on Discord real quick, Naya. We'll take a look at that. I think I can get that done pretty quickly. Send me your RMD. And I might take a quick look at it and show you like how to make it look pretty. It's pretty tricky sometimes to make it look nice because sometimes really big decision trees are messy. And I'll show you the fancy R plot thing that I was talking about in class today. But send that. And so here is the z-score of 1.96. And we're going to plug that into our equation. And we've got all of our notation written down. The more you do these like a step-by-step method, the better you will get results on solving them. You want to write down all your notation, know what the notation means. Great job right there, Ashling and Kayla. Excellent work. Go. Awesome. Yeah, it doesn't look the prettiest sometimes. They're hard to make to look pretty. Big decision trees are messy, messy, messy. Don't love them when they... Sorry, decision trees. Divide by 1050. Square root times by 1.96. There we go. What'd we just find? Timesing all that right there, we just found the what? The margin of error. Oh, it's blurry. I'll show you some tricks for that here in a second, because... It's definitely like adjusting the zoom and using fancy R plot can make things look nicer. The margin of error is it 1 as a percent? What's it 1 as? Percent. So we're going to times this by 100 right here. 1.78. So that's 1.78. That's the margin of error. 9.62. 9.62, 1.78. So 9.62 plus 1.78, 11.4. 9.62 minus 1.78, 7.84. We're just solving it out by doing the adding and subtracting. So now we have some interpretation. Explain what this interval means. I am 95% confident the true proportion of people who will respond to the mailer is contained in the interval blank to blank. Oh, good. HTTP. Let's hop to some 474 in a second right here. Like it. We'll do, let me see right here. I got a lot of questions. Thank you so much, everyone showing up right here. Hashtag show up. The 95% confident, the company is 95% confident that the percent of people who will respond to the flyer is contained within the interval. Yes. I am 95% confident the true proportion of people who will respond to this flyer is contained in the interval. Explain what 95% confidence means. 95% of random samples will produce intervals that contain the true proportion. Just some more theory on what it means to be 95% confident right here. 95% of 95% confidence are expected to contain the truth in the long run. So that's some theory right there. The company must decide whether to do it. Do they think they'll get a 4%? Do you think this company will decide to do it? Does the company think they'll get at least 4% response rate? Now be careful, it's not that they will get 4%, they want to get at least 4% of people responding to this, and then it'll be worth their while. So they did like this preliminary thing to see if they can get 4%. Does the company have good evidence that they'll get at least 4%? Which would mean they would do the flyer thing. And no, it's not that they're going to get 4%, it's that they're going to get at least 4%. Do they have evidence that they'd get at least 4%? Think about what that means. Does the company have good evidence up here? Oh, Snay is helping out. Love it. Does the company have good evidence that they'll get at least 4% with this interval up here? And why or why not? You can just simply say yes or no to the question to begin with. The company wants to get at least 4%. And they look at this interval here and say that they say, I think probably between about 7.84 to 11.4% of people will respond with 95% confidence. If we do this, like that's the true proportion of people who'd actually respond to this. Like if we sent it out to everyone on our mailing list, maybe a mailing list of like, you see right here, 200,000 people. And so with this right here, I would say the company has good evidence. They should do the mass mailing because 4% is not contained in the interval, which in a good way, it's above it. Like the interval itself is above 4%. So we think we're going to get at least 4%. I think we're probably going to get around 7.84 to 11.4% of people responding when we send this out to 200,000 people. Now, this 200,000 is used to check the 10% condition. This random sample we have of 1,050 people is less than 10% of the 200,000. So we could use that to check, random, less than 10% of the population was selected. And then we do see here there's at least 10 successes, and the failures would be 951 or 949. I think that's got it. Don't tell me oh my gosh. Did I get a number wrong? No, okay, let's find out. I think I did a rounding. Oh, what did I do with my rounding, everybody? Let's check it out. No. Did anyone see my rounding issue? That's my question says 4%. Let me check my rounding. 9.62, 1.7. So it's saying there's a rounding issue, it looks like. Do you see it? This is when you email Brian. So my question asks if we get at least 4%. Do you see the issue? Frankie right there. Frankie, 100 points. Will it give it to me now? Oh, I'll just put another 0 on. Oh, take that, my Pearson. Oh, round to 1 decimal. Oh, I was like, what did I do? I carried everything. Okay, let's take a look. We're going to take a look at Snape's question here. We'll hop back some 201. 201, hang on. We're going to go a little overtime and office hours today. Let's hop back. That feeling when my Pearson... That feeling when my Pearson tells you you're wrong. Let's go take a look at the Discord question here. Why is my things are all crazy? Oh, let's go take a look at the Discord. Okay, wait. Oh, that's R. Here's Discord. Snea sent the message. Here it is. Which part are you working on, Snea? Which line of code are you on? You said you're trying to plot it. Visualize tree right here. Got it. Let me run all your code above. So this is really great here. So this is going to be on visualizing trees. Explain with the S. Frank, you kill me, man. I love it. Excellent stuff right there. We're going to do some more tool on here in a second. Little 474 right now. So we're going to look at a tree-based model. And this is just a basic tree. It's not using the train function. It's just using the basic R-part method to make the tree right here, which it walks you through. So I'm going to run it right here. I'm going to visualize it. And it is blurry. I'm going to show you my way I like to visualize my trees. Ooh, it's very blurry. I'm going to add some extra code right here and show it here in a second. Okay. Looks better. Let's take a look at the better way to plot trees and how trees look. Let's take a look at it right here. So here is the blurry. Cannot see it at all. Here's the not so blurry method. So what I have right here is the rattle library. I don't know why they call it rattle. You want to install packages rattle. Do not try to knit these things ever. That's Control-Shift-C to comment out code. If you try to knit and install packages, it won't knit. But this here makes it way easier to see. You can also see the classification a lot better at the bottom of the tree to see right here the percent we have that are no, yes, and also has the percent of data in each leaf. This is a much bigger leaf. Stat 201, 500 points. If you can tell me, what do you think this this class is currently doing? As you look through this, and we asked people, what are their total daily minutes? Are they above or below a certain threshold? Like these people have less than 264 minutes. The number of calls they would have to customer service are less than 3.5. And we're asking if people will leave their cell phone provider. The people who are most likely to leave. Yeah, I know, right? And you can zoom in right here to make it even bigger and much, much easier to read right here. So if you're looking at this, this shouldn't quite answer the lab questions right here, but you can see each of the terminal leaves down here. Are those is that the number of observations? It says 5 right there. 1, 2, I think it's telling the order it was done. Yes, the order the splits were done. I don't usually look at that. So when you look at this right here, it does tell you the percent of observations, like 100% of the data values are up here. That is fancy rplot, a really good way to visualize stuff. Fancy rplot tree. I don't think, you know, I'm always going to try this. No, it didn't do it. Nah. If it did it, I'd have been like, what? If we could like hover over and do things with a ggplotly. Don't add a ggplotly. It just doesn't do anything. Doesn't do anything. It's not ggplottable. We're always asking that question, but can we ggplot it? So much better way of viewing the trees right here. I know, right? But can it be ggplotted? Can it be ggplotlied? And so this 5% means 5% of the observations. I will throw 500 points if a Stat 201er tells me what topic this class is learning. I'll throw 100 points if 474 says it in the Stat 201 knowledge, because Stat 201 has done this, but we're doing this at a more advanced level. But 201, this looks a lot like something you've done. It still looks blurry. Frankie sees it 100% right there. Yep, I think we're going to look at that next, Mohammed. You bet. Right there, Frankie sees it. This is a coded decision tree predicting, and that's what we're doing for the advanced classes, is we're doing decision trees, and we can actually do a lot more controlling on them and actually make tons and tons of trees with code. So if you're ever wondering, like, what we learned in 201, does it carry over? The whole idea is about decision trees and how they're done. We actually show the calculations and go, like, we do some of these calculations by hand, but the code does a lot of the work for us. Like, the code is doing so much work figuring out the right way to split these trees and how much we should grow the tree. So we're just asking, you know, here's our tree, we keep growing it, and then we learn about how we mathematically do these things with the sums of squared error we were talking about this day in class, or the impurity of the leaves. So you actually get into, like, 201, you just see how to use these things, and then the upper level classes, you get into the actual mathematical calculations for, like, what is the error here? I'll throw another 200 points, really quick on this, then we're going to do Mohammed's question next. All we're figuring out here, this error in 201 language is just a what? It's the, I'll give you a hint, it's the actual minus the predicted. The predicted right here being the naive. 474 should know that. That's the naive right here because it's the mean of the leaf, which is our prediction using the naive model. Kayla got it right there. Kayla, you're totally right. It's just a residual. You heard it. And this is how the topics carry over through each of these. This is a residual. And think about this. A residual is an error. And what are we going to do? We're going to square these errors. So this is the sum of the squared error. So when we say the sum of the squared error, we're actually just using a residual, squaring it, and then finding the sum of those squared errors. So we try to learn these topics more so than just memorizing mathematical formulas, but to understand why we're doing a sums of squared errors. How much do we miss by? And then why don't we just add them? Because they would add to 0. Goes back to 201 topics. Let's see here. Mohammed's got a question. We'll do that next right here. Let's do it. Thank you, everybody. Great questions today. Really love the decision tree stuff, or the partition models. So we call them partition models, classification trees, or regression trees. So many, everyone's got different words. Mohammed's question was 470. Oh, it's 475, is it? 475, Mohammed said. Sorry, I thought it was 474. Can we look at question 1, part C in 475? I thought it was 471. Let's go look at some 475. 475. I'm going to pull it up right here. We should be back. We should be able to do 2 more questions here. Thank you, everybody, hanging out. 475. Time series regression. So 320. Okay, let's take a look. Some 475. Question 1, part C. So we don't want to do too much right here. Let's not do too much. Let's talk about what's going on here. Kind of leaves some mystery. Okay. Let's hop into this. Some 475, making predictions. Talking about regression again. Here we go. No point sound. Oh, no point sound. Should be on. Oh, because I gave the 500. Yeah. There's some points on for you. Let's do it. So when we take a look at this right here, and I want to say this, the book, after this question, yep, I think we can do it next. Yep, I think Tiffany, I think we'll have enough time. Just enough time. What we're doing right here is we're using a data set. We're using the Australia electricity data set. Extract the January 2014 electric demand, aggregate this data to daily with daily total demands and maximum temperatures. You'll want to use the filter, the index by, and the summary. Okay. Woo, lots of fun for this. Let's do a little bit. I'll set up the data right here. We'll go into parts of this, and we'll look at the predictions. But what I want to say is, if you're looking for really great help for this, so the number one thing to do is the book is absolutely amazing, because I don't want to quite work the full problems. I think for a lot of times for the upper level classes, I try not to work all the problem. But right here, this is the forecasting principles and practices. This book is absolutely amazing. I should put it as one of MuBot's links. But the FPP3 book, absolutely amazing. And it's a completely free book by this gentleman right here. So thank you to him for coming out with this book, making it completely free. And we're doing time series regression models right now. And he's also got the search feature up here. And if we go into here and we take a look, let's go take a look right here. We want to take, and let's use the index by and take where we're going to do some code based on that. And nope, really? He doesn't do any indexing by ever? I highly doubt that. Here's the exercises right here. There's the index by right there. Very, ooh, I'm just saying right here. Oh, good. Nice job. What do you notice right here? I wanted to point out this hint right here, which maybe there's some hints. When you're looking through right here, which maybe for C, there's some hints. The book is a huge help. The book is a huge help. A lot of these times we're doing is based on the book. So for this first part right here, yeah, I'm not saying. But I'm saying right here, we're setting up the data right here. Let's go take a look. Let's jump back into this. And let's look at the procedure right here. So with this, we have Jan 14th Victorian electric data. What is... I know, right? Basically drop some huge... I like to drop the biggest hints first. Like get people over the biggest hurdles. But let's see what this is doing. Let's take a look. So with this code right here, we got here that we are filtering it, that we're taking only, and this is the time right here, we're taking only times that are equal to January 14th, January 2014. I can't even speak today. So this is the January 2014 data. We're filtering it here. And what I want you to do is this. Don't run this whole thing. Never run everything all at once. So let's not run this all at once. Let's run this. We don't have this because we don't have FPP3 loaded up, I think. So let's load up some FPP3. And there you go. And now you run this, and we have the January 14th data. I'm going to even remove it down smaller to this. Here is the January 14th data. So this is the January 14th data right here. I'd run this in those little bits. So now we're going to take and let's add to it. That's the January 14th. Let's index it by time. And let's go here and take a look. Here's the index by time. So if you did save this, I'm just going to save this as X at the moment. And we take a look at the index of X. Then you'll see the index of X is time. I wonder if it would have. I thought it was find index, but that's just setting the index. I would think logically it already has the index in there. It's fine. I don't see why we need to re-index it, but we're just setting the index. Last but not least, we're doing a summarize by here, which is going to create a table. So if you notice right here, we have demand is the sum of demand, and the temperature is the sum of temperature. So let's look at the final product right here, and here's what we get. Now, the reason we're doing this is because the data is originally collected by half hour. So if you look at the time right here, it's every half hour they're taking the demand and the temperature. So they take the temperature outside and then how much electricity people are using. You need to know the context for what data you're using. So this is in Victoria, not England, it's Australia. Everything's Australia with this because that's where Rob Hindman's from. And so we are looking at the hourly demand and electricity usage for Victoria right here, which I think is a province or something in Australia. I have to ask my friend Cody, who's over there. And we'll solve this, or we'll save this over here as elect data. And it doesn't matter what we call it. Called it this over here. Something's looking a bit different. Something's looking a bit different. Did I remove out something at the end? Oh, I think I just rewrote this, and yeah. Everything's fine. And does this make sense right here? If we are summarizing and summing up right here, then what are we getting right here? We're getting data for each what? And the answer should be there. Just think about what you have now. Why are we creating this? What does this mean? We are creating a data set for the what and the what for each what. What have we created right here? By summarizing and doing the sum. So we have right here, we took the max temperature on a certain something, and we took the sum of something on a certain something, and we're doing it by what? I might not even call it temperature. I might call it that. I think it makes more sense. Kale, 100 points. Yep. So we had a data set that was really big. So here's a huge data set. Imagine doing this by hand. Imagine if someone said, I need you to find me the max temperature on a day and the total amount of demand that was used, like the total amount of electricity demand. This would take a lot of time to go through here and sum up each one by day to be like, okay, this is at 2 in the morning on January 1st. There was this much electricity usage and this was the temperature outside. Or no, we can just summarize and find out on January 1st, the total demand usage. So we might not even call that demand. We might just go here and go total.demand. And that you just always think how to make these things make more sense. Like, exactly. Yep. Every 30. So it was every 30 minutes. Now we know the total demand on that day and the max temperature. And if you look at this coding right here, hopefully it's making sense that this is the name I'm giving it and this is the function I'm using to find it. So each one of these parts right here, think of it as like those Nerf blasters that you can put like modules on and you can add things to. You're just adding things. You're saying, here's my data. Only give me January 14th. So that's where we're filtering only that data. Then we're saying make sure the index, which is how we're doing the time, is by the time value right here. It's taking that as a date. And then we're summarizing it into a table right here, which you can see is the elect data, I called it. So we got a bunch of plotting right here. Plot the data and find the regression model for which demand temperature is my variable. Why is there a positive relationship? Use the TLSM when fitting this right here. So we're going to probably do just a tiny bit more of this when we get to Tiffany's question. I know, Mohammed, you're asking about C, but C is kind of contingent upon all of these right here. So it'd be hard to, I want to start people out on this assignment. And when you get down here to C with making the predictions, definitely check out the book right here. The book has so many good hints. The book has so much good stuff going on. And so why is it called TSLM? Why is it called TSLM? What do you think the LM stands for? What kind of model do you think we're fitting? What do you think kind of model we're fitting right here? Mine will have to be a little bit different. What kind of model do you think we're fitting? That's the hint. What do you think is called TSLM? It's a linear model. Kayla just crushing it. It's a linear model, and the TS stands for time series linear model. Put two together, and you're making a time series linear model. And frankly, actually, this might just be the code. I'm just saying the book has a lot of hints right here. So there we go. Are the next day scenarios right here? We don't have. Oh, you know what? See, I should be good if this is given to you. And see, it's going to cause problems. Brian's already making problems. Since the code is contingent on other codes, you might want to watch out because we're making predictions for new data where the temperature was 15, and we're going to predict demand. So we have to watch out. We're making new data right here for one of the Victorian. So this will add on to, I believe, onto it one new variable right here. Let's go look at it. 3 variables right here. But it's going to allow us to make these predictions right here. Double check. Next day. It's next day. So the next day is going to allow us to make these predictions right here. There's the data. And we have 2 days in here that we can make predictions on. So we are going to make these predictions on the 2 day. Hey, Wilson, good to see you here. We're going to use this model to make predictions. We can look at the residuals. Let's go look at that time series model. Do I still have it saved? I think we got it mostly saved. Where was parting? Plot the model. No. Where did I take that model? So we've got right here, we're piping in the new data we just created. And let's go look at the code right here. I think this is mostly what we want. Are we mutating? Plot the data and find the regression model for demand with temperature as an explanatory variable. Why is there a positive relationship? So we're not going to do any of this forecasting stuff yet. So this right here is for later. Let's take and remove out all of this. Once again, it's just like a Nerf blaster. We're just going to take and remove all this off right here. Because right now we're just piping in our data. Remember, this is just the data we have. All that is the data. That's not our data yet. Plot the data. So we don't want to plot that data. Oh, I think we want the Jan. So let's go over here. Oh, that is the Jan. I think I overwrote it by accident. There we go. That is the Jan data right there. We're going to make a model right here. So the model function makes our models. We're going to do demand predicted by temperature. So this is the y tilde x. And then we're going to auto plot it. And we should be able to get it. It says it's mad. Data not supported by auto plot. Oh no, of course there's a problem. There's always a problem. Let's not put this in here. It's still mad at us. Did it make our time series model? It is making the time series model. Let's go right here to the fit. Object fit not found. Oh, because I subtracted it. Stored as a fit. Auto plot. Object. Really? What is it mad about today? Who knows what it's mad about? It's always mad about something. We're going to hop here into a little more 201 after this. Oh, we need to forecast. So we should be able to, you get the fit. Forecast for the fit. I think my forecast is being overlapped by something real quick. Forecast right here. So we should be able to do the forecast. Is it not? It should like it. Let me go look at the forecast again. I don't want to mutate. Here we go. Well, it should just... And then there's the report. Good to see you here. What is it mad about is always the question. Augment fit. Augment fit? Really? And let's just take a look at this right here. So augment fit. ggplot aesthetic. We're predicting demand. Oh, got something. Temperature. What is it mad about? It is mad about something, but we'll find it. We're going to take a moment more. We got just enough time to do a stat 201 after this. We're going to make this plot up here nice and neat. What is it mad about? There it is. There's the ggplot. We'll grab this one. And we don't need the colors, so we should be good on this. So augment, fit beer, aesthetic. Okay, cool. So we're not going to do the full thing. I'm going to take this code right here. I think it's trying to... It might be the linear models creating a bit of an issue. Okay. So we're going to take our fit, the aesthetic. We don't need the color because we don't have a color variable on here. And so this is the end of the ggplotly. And we're not going to worry about our x. Our y is the demand. Oh, it says the fitted. We'll worry about that. And the x is demand. There we go. Yeah, no, it's exactly. Kayla, you're seeing it right here. We're predicting the demand right here. It's a little bit weird, and it says beer production and all that stuff right now, but here's our model, and we can make this look a good bit better if we want, and this is what I absolutely love about these types of things, is we could take all this right here by taking and plotting our model, and if you look at this, this looks just like what you were doing in 201 or 320 if you're in either one of those classes. So we go right here. My favorite thing to do is we can make, and that it doesn't have the right titles, we can fix all that up. But we get right here a pretty nice graphic pretty quickly, and we can see the model making predictions. And so you would fix this up, make sure we've got the actual values and the fitted values right here. We can see how our model's making predictions. And overall, I mean, does this look like a good regression model to you? QQ straight enough, no outliers, plot doesn't thicken? I'd say this looks like a pretty good regression model to me, because we have here a pretty straight relationship between what we would predict and what we expect or what we saw. And we see here that there's not any real extreme outliers. This has very good heteroscedasticity. Looks like there was some days where the demand was pretty high, like maybe it was a really cold day, like there was a cold few days in a row. It'd be interesting to see, but the model's doing a pretty good job. It's just that there was maybe like a snowstorm or something like that that increased the demand for electricity. But the model does a pretty good, consistent job of making predictions right here. And I'd say, yeah, pretty good model. Will the accuracy work on this? I am interested in the accuracy of the fit. Yes, it does give the accuracy. And what do you notice right here? Stats 201. Do we get? Oh, we don't get that value? Oh, it's a bummer. We get here the RMSE, so 320 should know this. When predicting the demand, we're typically off by about 23,732, and that's the typical miss we would make when predicting demand. So I do want you to know this, 475, if you're working on this right now, the book has so many good things. And we could fix this up right here to change what these values are. Like we want to actually say like daily electricity usage and change up the plot right here and actually make it look a lot better so we can actually see what's going on. But think about the way you're presenting these things. You could screenshot this and take a really nice looking plot and yeah, just make your values look great and get it working. With that, let's head back. I think Tiffany had one more question right here. Let's hop back to some 201. It's all about getting that code to work. And really, like, these functions are pretty crazy. Like, what you can do with piping everything through. Really good stuff. And the new data right there, making predictions with the new data. I'm going to kind of leave that. Kind of want to show what the book had because there's so many good little things right there. So we'll be showing that again later today. But the book has so many hints for how to do things. And, like, look at their examples of how they did it. And then have it work for your data. Lots of stuff right there. Tiffany's question was... which one? Tiffany said, do you have time? And the question was... Tiffany's question is... continue. Wait, here it is. In the 1980s, you're going to believe that congenital abnormalities... So in the 1980s, it was generally believed that congenital abnormalities... So let's go find that out. That is chapter 15, testing proportions. Do it a little bit quick here. So follow along. And thank you, everybody. We've already ended, but we are going on. In the 1980s, congenital abnormalities. Here we go. In the 1980s, congenital abnormalities. Yep, I'll be doing some afternoon office hours. Come back and we'll do some more chapter 14. Let's check out this question. In the 1980s, congenital abnormalities. Here we go. Now, we talked about this earlier. The null always has the equal sign. But they're trying to trick you right here because all of these have an equal sign. The null says that the true proportion is equal to this. The null says the true proportion is equal to this. All of these have the equal sign, so they all meet that standard of the null has the equal sign. But the null is always equal to our hypothesized proportion. They believe it's equal to 8%. So that's what we are hypothesizing is true currently. So the null hypothesis would be, it might be, it won't be B. So the null hypothesis is that it's equal to 8%. And then some people believe that this number is increasing due to chemicals. So when we say some people think it's increasing, we are going to talk about the alternative. And so the null would be that it's currently 8%, but we're looking for evidence it's increased. Does that make sense? So the way you know the sign right here for this is the way the question, great, Kayla, great job. And the way we know the sign is the way the question asks it. Does that make sense? Like some people believe it's increasing. So is the true proportion greater than 8% currently? So that's how we would know which sign to use is we look at the question and it says, some people think it's increasing. So is the true proportion of genital abnormalities increasing? So I'll read the alternative states that the true proportion of congenital abnormalities is increasing from 8%. So it will be, oh, did I click E? No, it'll be F, sorry. It'll be F because of the increasing. So some people believe it's increasing. Is there strong evidence this risk has increased? So usually you see the word evidence right here, and evidence is along with the alternative. So is there evidence that this risk has increased? And that right there says the proportion of children with congenital abnormalities has increased from 8%. Exactly. We're starting out assuming it is 8%, and we're looking to see if there's evidence it's more than 8%. Null, the conditions are going to be random. So we need to have that it was randomly selected, which also means independent. We want less than 10% of the population. And then we need at least 10 successes and at least 10 failures. If 8% is true, then 8% of the 423 would be 33.84 successes. That was NP naught times NQ naught, or NP naught is greater than or equal to 10, and NQ naught is also going to be because it's a bigger number. So we have at least 10 successes, at least 10 failures. Sorry, I'm doing a little bit quickly right here because I teach in 22 minutes. Or, yeah, 22, I think. Perform the mechanics of the test. This is where it gets a little bit tricky. This is where we need to do a lot of work, and it really does a lot of steps right here. So the mechanics of this test are as follows. We need to write the equation for the test defined the results. We need to write Z equals the observed sample proportion. Was it all of them? I think it was, right? I think it was all of them, right? Yep, it's all of them. There, yep. Good. Thank you, Kayla, right there, helping out. P naught. Oh, what'd I do? P naught times Q naught over N square root. P naught times Q naught over N square root. So now, they believe it's 8%. That makes this P naught. That makes Q naught 1 minus that, which is 0.92. Remember that P naught and Q naught are equal to complements of each other. So just 1 minus P naught is Q naught. They work the same as P and Q, P hat, Q hat, but it means hypothesized. And it'll be 0.08, or 8% or 0.08. So we use it as a proportion, so 0.08. Great job right there, Kayla. Keep going. And so now we have 423, which is going to be the sample size, and there is X. So X over N equals P hat. P hat is equal to 60 out of the 423. And this is equal to about 14%. Wow, 14.2. We're just going to write that over here, 0.14183, I think. And that is the sample proportion right here. That is the sample proportion. In our sample, yeah, very similar, right? Very, very similar to what we've been doing repeatedly. That is the sample proportion. Yep, same notation right here. Notation. That's why I keep saying you got to know the notation. You got to know, like, out of the 423, which is the sample size, we observe X amount. So that's going to be P hat right here. So that is the P hat. Now we're just going to take these numbers and solve right here. So mark your notation and then solve out 0.14184 minus 0.08 divide by, this is going to standardize it now, so it puts it in context. 4, 2, 3, and try to carry all the decimals till the end. So what I usually do is I have it in my calculator here, even though I'm writing it. I usually carry all these. So Like I'll solve the bottom right here. So 0.08 times 0.92. If you think there's a rounding issue, tell me, but the T stuff has a lot of stuff that's not rounding issues. Like people just don't use the T statistic. So sometimes we only say I was off by just a few hundredths, and it's like, oh, but you didn't use the right T, I think. Because the T chapter, you have to use the T. So this right here is the standard deviation. It's on the bottom. And 0.14184 minus 0.08. And there's the T statistic. T statistic is, or Z statistic is pretty large right here. Pretty crazy Z statistic. Pretty crazy. 4.69. That's ridiculous. Can you tell me what the p-value is going to be? I'm going to show you what the curve looks like. 1, 2, 3, 4. Can anyone estimate the p-value for me? Can you estimate the p-value? That shaded area is the p-value. Remember, we're doing a greater than test. Since the alternative had a greater than sign in it, the alternative was p greater than, which means we shade to the right. So just give me an estimate of that p-value right there. We'll show it on the David M. Lane. We don't have a David M. Lane. Oh, we do have a David M. Lane open. If you got an answer of that, you're going to shade to the right, and yours is going to be very close to 0.002. I'd say yours is 0.002, Tiffany. Tiffany's is probably about 0.002. And there it is. It's going to round to 0.002. Now mine is further over. And we're shading to the right because it's a greater than test. Mine is further over. So what do you think my p-value will basically be? Mine is 4.69. So mine is way off the edge of the curve. So how much area is above mine, which is the p-value? How much area is above mine, which is the p-value? Just think when I click this, even less. Basically, nothing. Does that make it's off the curve? It's like it's over here. You can't even see it. So it's very little next to nothing. You can't even see it. Tiffany's was over here where we could kind of see it. Let me enter in Tiffany's decimals again. 9695. You can see where Tiffany landed right here at 2.96. I'm blocking it. 2.9695 is right there. And so yeah, my number though is way off the edge of the curve. If we wanted to estimate my p-value, we'd have to go over here into R, and we'd have to say p norm 1 minus p norm 4.69, and that's the area above it. If you just run this, you get the area below it. So that's the area below it, but if you do 1 minus, you'd get the area above it. So there's this, that's the p-value. Very, very ridiculously small p-value, and that's the reason we don't see it, because it's way off the curve. You can't see 4.6, it's over here somewhere. So I did a little bit of a drawing and didn't even give it enough context because it's actually further over than just 4. It's 4.69. So that's why the p-value is so crazy small. Please check out. This one's basically 0 for mine. Yours might not be. It's because my z-score was so small. Explain what the p-value means in the context. It would be the probability of observing this many or more extreme by random chance, given 8% is true. The p-value is the chance of observing 60 or more children with genetic abnormalities in random sample 423 if 8% is true. What is your conclusion? The p-value is very, very small. We reject the null hypothesis. There is evidence for the alternative that more than 8%. Does this mean anything causes it? What do we know about statistics? A few people got this wrong, and I was like, no! Statistics never does what unless we do some sort of experiment. Unless you do an experiment, statistics cannot show this. Statistics cannot show this C word. Statistics cannot show what? I think it's the right answer, actually. Statistics, it is unknown if they can't show causation. Unless you do an experiment. Experiments can control for things and do random assignment. But experiments can give good evidence of causation. This is not an experiment. So the cause word throughout our class is very bad. We don't like to say things cause things. Let's cross our fingers. Not today, Ma Pearson. Because the hypothesis, it is unknown. I was like, Ma Pearson, you don't do that to me today. You don't tell me I get anything wrong. I was a little bit worried because the hypothesis test does not indicate the cause of it. Yeah, it doesn't. Should say this is not an experiment. Like a better answer would be, it is unknown if environmental chemicals cause genetic abnormalities because this is not an experiment. But then you have to know experiments are about random assignment, control, and test groups. So the real way would be to do random trials right here. Yep, random assignment, all that good stuff. So anyways, that's got it. Excellent work today, everybody. Check it out. Swing by the afternoon office hours if you got questions. But really good work. A lot of topics covered. Woo! Busy office hours. We'll have more busy office hours later here on Stats 101. 320. I'll be seeing you soon for some more regression. Let's go check it out. Almost out of coffee.